Okay, we are going to look at lesson 4 today. So the end of this lesson, we're going to do a little bit of a screencastify. I'm going to transition to showing you something on a graph at the end. So if you're not seeing the comparison between quadratic and exponential growth here, or if the math is confusing, stay with me. I'll show you visuals on a graph on the computer at the end. So first part should be no problem. List these quantities in orders from least to greatest. Try not to actually find out the value of each. Like, you might know what this value is or what this value is, but try to reason through which one would have to be the least and which one would have to be the greatest. Okay, so we should know that 9 squared is less than 10 squared, and that 2 to the 9th is going to be less than 2 to the 10th. So we really want to figure out is which sort of set is going to be less than the others. If I multiply 2 by itself 9 times, is that going to be less than multiplying 9 by itself twice? And it turns out, so we might know that 9 by 9 is 81, or that 10 squared is 100. But if we do 2 times 2, 9 times, let's see, 2 times 2 is 4, times 2 is 8, then 16, then 32, then 64, and eventually, now at this point now I'm over 100, and I've only done 2 to the 7th. So even if I'm not calculating all the way, I still know that 2 to the 9th has to be bigger than 9 squared and 10 squared. So this is my order from least to greatest. All right. So we're going to compare quadratic and exponential functions today and see which one tends to grow faster. And we're going to get a little hint at that to see when you notice that 2 to the 10th, if the bigger exponent of 10, so the exponent's 10 here, and the base is 2. Compared to the base being 10, the exponent 2. We're going to find that the bigger exponent seems to actually take more precedent than the bigger base in this case. And we'll see a couple examples where that happens today. So here we have a couple patterns. We have pattern A, and we have pattern B. All right, and this one says the length and the width of the rectangle grow by one small square from each step to the next. So my length goes up 1 and my width goes up 1. And in pattern B, the number of small squares doubles from each step to the next. So you have two different patterns going on. So first, we want to think about, is each pattern linear, quadratic, or exponential? Linear, quadratic, or exponential? Then figure out how many small squares are in each pattern after n steps. And you can honestly do that probably independently. And even number 3, I want you to give a try to on your own. Try to do all of this independently. All right? And to do this, you might have to find step 4, step 5, step 6. All right, but just follow the directions they give you to do that. So this is the part of the video where you pause to do this on your own. Okay, so here's my patterns. I drew step 4. At least for the second one, step 5 would have been very large, so I did not do that. So notice that in the first pattern A, we're just making larger and larger squares. So it was 1 by 1, then it was 2 by 2, then it was 3 by 3, and 4 by 4. And then step 5 would have been 5 by 5. So eventually, that's really just squaring a number. That's really just length times width being the same. That's really the area of a square. So that one is going to be quadratic, because I have to do the side length squared. I'm squaring the sides to get to the next number. And I can tell it's quadratic because in my thing, remember, quadratic doesn't go up by the same amount every time, but the amount it goes up is linear. So that went up 2, that went up 2, that went up 2, and that went up 2. So even though I'm going up by more and more each time, it's not linear. It's also not exponential, though, because there's no common growth factor. The amount it's growing by stays constant. All right? And my formula involves squaring a number. To find f of n, part of that formula, or that entire formula in this case, is just squaring a number, n squared. So that's how I know it's quadratic. And is the function linear, quadratic, or exponential for this one? Well, this one is a classic case of last unit, where I'm doubling from each step to the next. So that's going to be exponential. That's exponential growth. And here we have a growth factor, because every time I'm doubling the amount of squares I have. So, in that rule, well, exponential function, our starting value is 1, and then we're doubling every time. I could have done 1 times 2 to the n, but really I want to just recognize that it's just 2 to the n power. All right, so there's those. And then how would these patterns compare if they continue to grow? Let's look at our tables. Which pattern's got more shapes in it? Well, pattern B maybe starts out a little bit less, maybe grows a bit slower. It starts out growing slower, but then it curves and has much more at the end, right? So pattern B had more, same, less, same, more. So pattern B is going to be much larger. Much more squares. And A will never catch up. All right. If you found other observations, go for it. That's really the whole gist of it, though, is that that exponential seems to grow faster. We're going to see if that actually remains true all day today. So the exponential is growing faster. So we're going to look at a couple more functions. We're going to look at p of x equals 8 times x squared, and q of x equals 2 to the x power. So notice, when you have 8 times x squared, evaluating p of x means do the x squared and then multiply by 8. Don't do 8 times x then squared. You do x squared and then multiply by 8. So that's why when x is 1, p of 1 is going to be 8 times 1 squared. Now the reason I like the parentheses there, because 1 squared is 1, and that's 8 times 1 gets me 8. Whereas 2 to the first power is just 2. So figure out the rest of these numbers. Now I want you to focus on which function will have a greater value as x increases. So at the very end, 1, 2, 5, 8, and do a couple more numbers after this. Which function will have the greater value? Okay, so here's our numbers. If we figure out p of 2, p of 5, p of 8, I did 9, 10, and 11 just so I could see how it grew and how eventually around x equals 10, we see that q of x is now greater than p of x for the first time ever. That's not true, but for the first time in numbers that we're seeing. So over here, it looks like p of x is greater, p of x is greater, greater, less. And oh my goodness, way less, right? So once you get up here, q of x is starting to really explode. All right, this exponential growth, things really start to double. Like people, like this starts to be really significant. So, yeah, we can sort of see again where you have quadratic growth. And notice real quick, the quadratic growth is still there. So like we're going up by 136, okay, up by 152 from 648 to 800, and up by 168 from 800 to 968. But still, it's going up by 16 more every time. It goes up by 16 more people every day. So then after 12, I would go up by 16 more than this number. So I can even predict where 12 would be. So 12 would be, let's see, what's 168 plus 16? That's like 184. Could have to go up 16 more. So then I could be, all right, so 8 plus 4 is 2, carry the 1, 6 plus 8 is 14, 15, carry the 1, 9 was 10, 11. So that would be 1152, just following my quadratic growth. It's going up 16 more than it previously did. And if I do 8 times 12 squared, if I do 8 times 12 squared, which is 8 times 144, let's see, all right, 800, 8 times 40 is 320, 8 times 4 is 32, so that'd be 1152. Yeah, it's like the same number. Anyway, that's one of my you got my math tangents still, even on video. Aren't you lucky? You still got my weird math tangents. But isn't that so cool? Like you can sort of predict what the next one's going to be just by following, well, it's going to go up 16 more than it previously did. And up here, it would have only gone up by, if you had 7 here, it would have only gone up by like 120 to figure out the 7. So if 7 was here, we'd get 300 and, no, yeah, 92, because it would have gone up by 16 less. All right? Anyway, fun fact. Okay, so we're going to get into visualizing this. Well, this is always true. Cormac says that some exponential functions must grow more slowly than quadratic function as x increases. So do you agree or disagree? Do you think that there are some exponential functions that might grow more slowly? Because we had 2 to the x, like, okay, doubling is a little bit, that's pretty dramatic. So are there some where it doesn't always catch up? So think about if there's any growth factors, which growth factors might go up slower than a quadratic. All right, think about that for a little bit, and then we'll show you like what that might look like on a graph online, all right? Here's our Desmos online calculator. You can see the link up here. You can actually use this to help you graph anything you want. Fun fact. And I'm not going to know if you use it or not, but I strongly recommend it for a lot of your assignments. If you have to like graph something, or if you're not sure what your graph looks like, feel free to go to this. It's desmos.com/calculator, as you can see up here. Okay, so we have the classic example from class where we had 2 to the x and x squared. So I'm going to use this slider. So this b is my growth factor, and we're going to just see what happens when we change the growth factor of b. So right now it's just 2 to the x, and we see that fairly quickly this becomes much larger than x squared. So the question was, is there ever a growth factor when b will always, where g of x, our exponential, will this ever be less than our quadratic? So the hypothesis is there are times when it is. So let's find some. So I know what you're thinking. Well, exponential functions only really work if b is greater than 0. And we're obviously not going to do anything bigger than 2. And I'll just make the step 0.05. Yeah, sure, I'll do that. That doesn't matter for you guys. Okay, so we have our 2 to the x. So let's see if we can change this growth factor. Now, I know what you're thinking. There were some cases where we had exponential decay. And if I had a growth factor less than 1, I had decay. So, like, okay, if b was less than 1, I definitely was less than in all values. Unless you go into the negatives, and then it turns out. But, well, that's back in time. That's a little bit scary to think about, so we're not going to do that. So we're going to deal strictly between b and 1. Or, I'm sorry, 1 and 2. So is there a growth factor that will always be less than quadratic? So let's think. So if I lower this growth factor, this is like getting into like increasing by 80% per year. That's what that is, like an 80% growth factor. So it's not quite doubling. And we notice that when we change to not quite doubling, it is going down. It is going down, it's going down. And sometimes it's getting a lot flatter, but we see that it looks like we might still intersect. And if I look at my graph, it does seem to be that, yeah, we intersect at like x equals 20, even if it's 0.35. So let's change this. Let's make it a lot lower. Let's make it like 0.2. Okay, will that ever intersect? Let's zoom out a bit. And it turns out, oh yeah, it does have that big steep incline eventually. And yes, it does intersect. Let's lower even more. 1.15, 1.05. All right, this has got to be good. 0.05, 5% interest. That's not very good. All right, we're getting there, but I still think that blue line is getting a bit steeper. And yes, they do still intersect up here. And granted, it takes a long time. It takes till x is nearly 222 to get there, and a y value of nearly 48,000, but it does eventually intersect, as you can see from the graph. So is that going to be true for all of them? Let's change this step to be 0.005. Let's go down even more. So let's change this even more, less, 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 less. Let's make it like a 1% interest. All right, this is so bad. Look at this. They can't possibly ever meet. Mr. Roboto, what are you doing to this graph? Hold on. Okay. That's not what I wanted to do. Are these lines ever going to meet? But it looks like they will. Let's keep scrolling up. They're going to meet. They're going to meet. They're getting closer and closer and closer. I'm going to change my x-axis to like way less. I'll change it to like, there we go. Okay. So we see that blue line is going up much more vertically now. And they're intersecting up there. This one, at 1% interest, took 1,400 x values to intersect. 1,400 months of that interest, and it finally passed. All right. Investors are always gonna be like, "Oh, well, you'll get your money back. You'll get your money back. It'll just take 1,000 years." So like, great, cool. So even okay, let's look at 1.005, a 0.5% interest. Will those ever intersect? And you can see, oh, this blue line right here is steeper. Yeah, they're gonna intersect at some point, and it's way up there. This is like scientific notation high now, 3,000 x values and nearly 1 million or 10 million in the y values. So long story short is exponential is pretty much always going to catch up eventually. I can make my step 0.00 and we'll add in a 1 there just to keep things fun. And I can make my step smaller and smaller and smaller. But you can see that vertical line. They will eventually cross. Trust me. It just might take a really long time. A really long time. Good grief. What am I doing? That's like half of a percent interest up here. Good golly. Good golly. Can't even see what I'm doing anymore. Oh, see, there they are. They've intersected right here. You can see it. The blue crossed the red right down here. So eventually, no matter what, those exponential functions will cross. Because here it's a little bit lower. And it's very hard to tell because lines are basically vertical. Let me shrink my x-axis. I'll go to from 40,000 to 50,000. 40,000. But see, we're dealing with x's in terms of 50,000. So I mean, like, clearly something's going on here. It's going to take a while, but it gets there. All right, and there we go. We can see it. Yep, blue was lower, and now blue is higher. So there's our proof. Cormac, unfortunately, unless you have exponential decay, your exponential functions will never always grow more slowly than quadratic. It's just the way exponents work. They just multiply faster. So that was your lesson for the day. I hope you enjoyed looking at the graphs and being handed something to always help you graph anything you want now. So there's no excuse to ever have graphs wrong because you've been given this lovely website. And oh look, your video for Monday is ready to be published. Awesome. Okay, so best of luck to you.